Okay, so let's look at the different modes of transfer. The way that this particular machine works, it has many different ways it can weld. I'm just going to list them here real quick. So first off, as we brought up before, we can use gas, we can use flux. Specifically, this flux is inside the wire. This is called flux cord. So it's actually like a little jelly-filled donut, just like so. Or we can use both of these. We would call this dual shield. Dual shield is just utilized not actually to prevent environmental conditions like wind. It's actually utilized to, we add a little bit of heat into the flux. We use an exothermic flux. So this flux here would be very hot. And then we use the shielding gas, usually argon, at a rate of 75%, and CO2 at 25%. And we use these two gases to help to shield that. The flux in that case with a dual shield is actually made to melt more metal. So we can actually throw more metal on the puddle that's used for really thick material. So 3 ways that we can run this machine: gas and no gas. So gas, these processes commonly have gas, metal, arc, welding. For their acronym, back in the day it was metal, inert, gas. So it's changed a little bit. If we're using a flux, the acronym for this usually is just flux cord, arc welding. Some people may mistakenly call this MIG, but it's not. Because MIG is metal inert gas, and there's no real inert gas. We're generating inert gas by burning the flux, but it's not provided for the puddle. And then dual shield. So this is just how do we want to shield the puddle. Then in addition to that, there are 5 different ways that we can shield, that we can actually make this machine work. We're going to do something called short circuit transfer. I'll go over each of these a little more in detail after I list them. Short circuit transfer, globular, spray. We can pulse this spray. And then something nowadays called cold metal transfer. So, and these right here are called modes of transfer. So, just like with stick welding, this particular machine, this particular process is a consumable process. That just means that the electrode ends up adding weight to the puddle, and we have to transfer that metal, that is wire, into the puddle. So different modes of transfer right here. Okay, so different ways we can shield them, and then different modes of transfer. So let's start off with the oldest, probably the most common technique. This process was originally used for lithium materials, a fairly inexpensive machine, and this is called short circuit transfer. Short circuit transfer. And this is for thin material. Maximum material that this can weld, maximum thickness is 1/4 of an inch. This process, the way that it works inherently, you just can't get any more heat across that envelope with the way this process is going. One machine could go hotter, but as it goes hotter, the way that the metal is crossing that envelope changes, and the way that metal crosses the envelope is called the mode of transfer. So maximum thickness, 1/4 of an inch, all position. This is all position welding process here. This one's very interesting because this one takes what we've learned from stick welding and then really exemplifies that. So keep in mind that this machine is constant voltage. We don't have control of the arc. If we keep this machine close, it makes this big of an arc. If we pull this gun back a little bit, it still makes this big of an arc. So here we cannot control the arc. This is the arc length. And it stays the same no matter what we do with the gun. What does change though is this little bit right here. And this new measurement is something called stick out. And it's just how far is this wire sticking out of the tip of the gun. Keep in mind, like we saw in the first video, we put electricity to it right here. So this part is just as much as we're electrifying right there. Very important concept now called stick out. No control of the arc length. Doesn't matter. We'll show you this in the third and final video. So how does this process work? Here's all the basic numerics of it. This process short circuits very, very quickly over and over and over again. So in other words, wire comes out of the gun. Wire hits the deck. It forms a little bit of an arc. This material that was here falls down into the puddle. So that's where we get it. Arc falls into the puddle during the arc. This wire comes down eventually again and hits the surface. And this whole system repeats. Boom, boom, boom. It actually puts the wire against the surface, forms the arc, forms the arc, forms the arc very, very quickly. If you see this actually happening, then your machine's set up too cold. So it happens very, very quickly. So consequently, what do we have here? So if you just look at our two variables, amperage and voltage. Right here, when the wire's hitting, we can get the maximum amperage across right here. So amperage goes up. Because there is no arc, voltage goes down. Voltage is right here. Then, as we come across, the arc is established, amperage drops, and voltage goes up. Voltage stays high during the arc, amperage stays fairly low. Then when they hit again, drops down again. Voltage then drops down again, not quite to zero, but it drops fairly low. And the amperage spikes up again to wherever the maximum setting is. So they're constantly going in opposite directions. This is a really important concept to note, that when the wire's connecting, we get the maximum amperage and we have the least amount of voltage. When there's an arc, we get less amperage across, but we get the most voltage. And that's because the voltage actually has to dump across that little area. As the arc continues, the voltage stays up, amperage stays relatively low. And then, boom, as we hit again, there's a full connection, amperage spikes, voltage drops. Very, very important concept. Because of this cycle here and this cycle here, the wire is hitting the surface very quickly. It allows the metal to have a very direct transfer. Because it fuses, it arcs, and it separates itself like this over and over again, this is where we get this short circuit aspect of it. Think of a fuse. Think of an old fuse, a glass fuse. They have these little steel cans, like so. Right? They're steel, and then they're glass in between. There's usually some sort of wire here. Right? This is an old fuse. You put too much electricity through this, you have less wiring here. And that's where they get this idea of short circuiting. When the arc is there, that's just like breaking a wire. That's where they get this name from. That is our first. That is probably the most commonly used. If you've done some MIG welding, it probably was short circuit transfer. Maximum 1/4 inch, just because as we're hitting that wire across, and it dips, 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 you just can't get any more material hot. Remember, it's very easy to get a .035, so we're using ER70S2. And in this case, it's round. It's only .035 of an inch, so this is steel. It doesn't take much heat to blow that wire apart. So thus it can't carry much heat either. We can't melt much material. If you turn this machine up, you crank up the voltage or you slow down the wire feed, you start saturating this stick out, this distance here. You start saturating this with heat. You don't do this by pulling the gun back. You just do this by either turning up the voltage really high, just like so, or slowing the wire down. If you slow the wire down, then it has to get very, very hot. Globular then comes into play. So make no mistake about it. There's nothing on this machine that says spray, globular, or short circuit. There is something that says pulsing, because that is a computer aspect that we throw on top of it. But there is nothing on this machine that says spray, or globular, or short circuit. These are just arc characteristics and how the material transfers across that envelope. Globular, the wire hits, the arc forms, the wire pulls back, the arc is here, all the heat is saturated in the wire. Keep in mind, this is DC, electrode positive, so the electrons will fly up and in this, and you end up with this globe, this ball that hangs right here. You can call it a globe as well. Eventually, the mass of this globe right here becomes too much, and that ball lets go and drops off, splash, with an impact. Then the process starts anew. Now the big arc forms, starts heating up this wire, you get this big ball on the end, boom, the ball falls off, hits into the puddle. Globular. The problem with this process, that ball is so large, magnetism's not going to control it. Small field, when we have a small wire, it's a small field. So this is straight gravity. We do, as we learned in the stick, because of this great drop, all of a sudden we do get a lot of heat, so we do get a little more thickness of material. This stuff is good for 1/8 of an inch up to about 5/16. So it's good for a little bit thicker material. A gravity-based only, so we're talking flat and kind of horizontal, a little messy. Not really a good process. They do use this very dedicatedly in some really in-position only fixtured welding, truck bodies, sheet metal projects, where they basically have an inexpensive short circuit transfer machine. They want to get a little more penetration, so they allow for this app. And it does make very distinctive ribs, really distinctive cooling pulls on your weld, so that's nice. So, but more of a mistake. Most people would find that as an accidental setting when they're trying to do short circuit transfer. And they just went too slow on the wire or too hot on the wire, and this is what happens. So it's more of a mistake. If you're welding and you're trying to do an out of position weld and it's dropping balls on you, you need to reduce the heat or speed up the wire. Just one or the other. It's going to catch your leathers on fire. It's going to burn you pretty bad. So if you're welding and your weld pool seems to have a hiss and a pop and a pop and a pop, that's globular. That's not made to go overhead and vertical. You're just going to catch on fire doing that. Spray. So this is kind of what we were all hoping for initially when they started these machines. A ton of wire, endless fill, and it's like 100 miles or something on these spools. It's tremendous. It's 50 pounds of rod right now. That's an entire box of stick welding. And actually it's probably about a box and a half worth of actual metal, because a lot of the material on a box itself is actually just the casing. So a lot of the material. You can lay this down for a very, very long time. Spray is really high voltage, high wire feed, and consequently high amperage. On this machine, you actually have the ability to adjust the voltage. Remember from the first lecture, you can adjust the voltage as the primary knob. And when you adjust the wire feed, that also plays, that will increase your amperage. If you increase the wire feed, it's going to increase your amperage as well too. So lots and lots of heat. When they first started this, they used very, very thick wire. So they were running 1/8 of an inch thick electrodes out of a machine called an L7. That is what we were running with our stick welding, so not very flexible. Not very flexible at all. Now, we are running what's called a lead shield. What this is a flux cord wire. And particularly the flux that we put inside this wire is very hot. So when it hits that arc, it gets going. It's not there to make shielding gas. It does make some incidental slag, which helps with the thermal properties, right? It helps it retard that cooling a little bit so we don't form martensite. So the flux that's inside of this actually generates heat. This is exothermic. Meaning it just generates heat. As we burn it, it makes more heat. So consequently, we're going to throw in a ton of this wire on the puddle to get the metal that we want and a ton of voltage. So very, very good process. Minimum thickness is 1/4 of an inch. If you have a thinner material, you absolutely, my students do this all the time, you will blow it straight onto the table. You will burn right through that material in about 3 seconds, and you will weld it straight to the table below it. So minimum 1/4 of an inch. So keep that in mind. And then position limitations, flat and horizontal. So let's look a little bit at the arc characteristics of this. The arc characteristics, this wire actually hits, pulls back, starts an arc, and then the material is literally heaved across the envelope in little droplets. It is literally sprayed onto the deck. So this is process is called spray. Spray welding. I try not to capitalize all that. I usually do. And the reason why I usually capitalize all the spray welding is because it's fairly dangerous. In my lab, this is a lab that I've set some pants on fire, some hair, papers nearby. This lab is inherently fairly dangerous. It throws a lot of material. This spray, not all those droplets end up there. They end up all over the place. But great process, very efficient, limited in its ability to weld out of position. You want to weld out of position, you got to strap a microprocessor on the front of that machine. That's called pulse spray. And all you're going to do there is you're going to maintain a background. You maintain a background voltage, and then spike it up and bring it back down. Spike it up, bring it back down. And these indications, these little bumps here, are your pulses. These aspects here are your peaks. That's when you actually have an active puddle you got to deal with. It's overhead or on a wall or something. These areas here cause the freezing. That's what allows for that puddle to actually cool and not land on your head. So we're just making this little hot weld, cool it down, hot, cool it down, hot, cool it down. Just getting that cycle in there so we can make this happen. Finally, with this process here, now with pulse spray, we can do really thin stuff. Depends on how thin the wire is. If you can run really, really thin wire, then you get that wire to behave in spray mode. You can get that really small wire to behave and get it really hot so it starts crossing an envelope, and then when that happens, you can make really small wire behave in well, very thin material. They're saying like 1/16 of an inch. You can use that pulsing and you actually cut down your heat factor by half. So you have half the joules going into this very, very easily. So down to 16th, and then thick, still quarter plus. By the time you get to a quarter, you can weld all thicknesses. Because you're only going to heat up so much material every time, so you can stack in your weld. So you can do 2-inch material, right? You just got to bevel the heck out of it. Come in here and stack in, you know. 2-inch material, I think, is on the neighborhood of 25 passes. You got a chip between every one of them, but you can get in there and do a lot of passes. So this is all thicknesses, really. That's how you can say that. And you can do this out of position. So this means vertical and overhead. Makes it very profitable. Which is good, because that machine is very expensive. So it's good to have it very profitable. Finally, and this is a new mode of transfer. And so this company, Fronius, Fronius, came up with this process. I think maybe over 5-6 years old now. So they've taken all these ideas that we've exposed you to. This idea that this increases the voltage, this increases the amperage. They've taken all these ideas and taken it really to the next level. I would strongly recommend you go to their website and check out some of their stuff, because I just can't give it enough justice. But let's give you a little bit of an idea. One of the big fail points in any wire feed machine is these two wheels. These two wheels grip our wire and push the wire. That is a bad picture. At the gun now, we're grabbing this wire and we're pulling it along. And so that's how it's now we get really, really thin wire. We didn't used to have that ability. So we have a little gun, and I showed this on the gun out there in the lab. This little gun has the feeders up here and drivers. Some companies now have added additional dummy wheels here, and these wheels can tell if these wheels here are doing their job. So these are just feedback loops. They're saying, yeah, the wire's going by. Because as the wire pushes, they rotate these wheels, and they know, okay, that wire's going by, we're good. We don't have anything else. And then these wheels up here will also drive it. And I'm not really sure. I haven't taken my saw, my knife, my tweezers to one of their machines, but they have built something into this machine to make it behave in a different manner. So this is what they're doing. They're taking the wire down. They're hitting against the surface. Amperage goes up. It gets very, very hot. They pull the wire back and introduce an arc. And I mean turn the arc on. It's not something that just happens because they pull back. A microprocessor turns it on and the arc gets going. They make this area hot right here. Then they take this wire, cut the arc, and they drive it back into the puddle. Fulp. Add as much material as they can until it stops. Resistance goes up. They pull back on this wire, which pops off a little bit of that wire, makes an arc again, and the whole process repeats. In addition to this, they can fire electrons. They can use this as electrode positive. So as they're turning this back, they can actually heat up this wire. They can fire electrons into it. Then when they're going down, they can turn this into electrode negative and fire electrons in and make that puddle. And then electrode positive, and they can pull this back again. I don't know where the wire goes. They must have an absorbent element in the gun that keeps it from jamming up in the back of the machine. I have no idea. I'd love to get one of these machines and take it apart. This is called cold metal transfer. Think of it as when I was TIG welding, I would make a puddle and then I'd add that cold metal to it, right, for my second hand. Not an electrode. We call it electrode, but we're not conducting current through it. It's just filler rod. Make a puddle, add cold metal to it. Make a puddle, add cold metal to it. Not only am I absorbing some of that heat here, so we're losing some heat from the puddle, but I've turned the arc on and off. So now the joules put in are very, very minimal. Where do they use this? Tesla. Since Tesla went to solid aluminum body cars, they're using this heavily. I wouldn't doubt if they were in cahoots to make this happen. Ford, now Chevy, even though they made all those jokes for years and years about Ford's aluminum trucks, they're having to suck it up and make their own aluminum trucks because of gas standards. So any number of people are using this now. This process can weld thick material together. It can weld thin material together. You may not know it, but one of the standards in welding forever has been, can you weld 2 beer cans together? Oh, amateur hour can weld 2 beer cans together with this machine now. It kind of took that off the table for us. Thick, thin. They even have a process now where they can weld aluminum to galvanized steel. Turns out they just make that zinc just hot enough to get it to flow it in with aluminum, get it to coalesce, boom, away they go. So now you have a piece of aluminum here, and steel, which has a better crush value, it can absorb more energy in an automotive, in a car situation than impact. They're welding these together and then crumpling them, and they're staying together. We'll see this on the video. This is where we're going in the future of welding. And it's all about just understanding this really interesting idea that when you're on the deck here, voltage is low. Amperage, again, is high. So these early concepts that we showed you with stick welding are coming back around. Fronius has another process you can see, it's called stud welding. And actually at this point in time, it's like little bits of wire welding. It's for composites and adhesives. Basic idea is this. You have a bridge. I'm just going to draw my version of the Golden Gate right here. Boom, 2 towers. South Tower. Over here is Sausalito. San Francisco. Over here is called Fort Point. Nice little wave inside of the San Francisco Bay. Actually comes in and breaks this way. Very nice. Nice left. Good for a goofy footer. Yeah. Okay, so you make your bridge deck. This is steel. On top of this bridge, they have to put asphalt concrete. And if you've driven across steel plates, you know, yeah, those are slippery. You're going to crash into somebody. When they do road work and they put down those steel plates, that's a problem. But you can't really put asphalt just straight on top of this. You put asphalt straight on top of steel, you get a bunch of cars on here, they all stop, and all this concrete slides across and wads up over here. Right? You can't just put a bunch of asphalt on top of concrete, on top of steel. It doesn't work. So what they do is they get these bolts that are like the size of my finger, which is probably 2 to 3 inches, and they shoot them on here, and they have heads on them too. This isn't to scale. And then they pour the concrete over that, and the bolts end up attaching, locking that concrete into place. So this is called projection stud welding. Very commonly used process, used in bridges. They also do it on rebar to keep concrete from coming off, such and so forth. What Fronius is doing now is they're actually taking that whole concept of amperage and voltage, and they move a gun over, they shoot down this very thick wire, they make a puddle, then they actually pull back hard on the gun and crank the amperage up, and this pops off. There's a little head right there. And then move the gun over to here, shoot the wire down onto the surface, hold the wire back as hard as they can. This is all mechanized. It's all in a big gantry, so it's not going anywhere. Crank up the amperage and it sears off again. And by doing this, they can shoot on little studs. So that amperage voltage concept is going to come back over and over again. I hope this helps to explain the modes of transfer, and they all too crazy wire feed machine. Remember, we can use it with any number of gases. We can have any different kinds of modes of transfer. There's a whole slew of acronyms, and I will include a diagram for you. Hope your day's going well.